So the topic that I am discussing to you is the anisotropy. So first, what is anisotropy? Anisotropy is the materials which changes properties with direction. So an example of anisotropy is the wood. Because when we apply different loads in different directions, it contains different values. So next, anisotropy. The anisotropy is the physical properties of single crystals of some substances depend on the crystallographic direction in which measurements are taken. So for example, the elastic modulus, the electrical conductivity, and the index of refraction may have different values in the different directions. So anisotropy is the property of substance to exhibit variations in physical properties along different molecular axes. It is seen in crystals, liquid crystals, and less commonly in liquids. So it is usually observed in crystals and liquid crystals. It is less commonly seen in liquids. It can also be defined as the difference when measured along different axes in a material's mechanical and physical properties. These include absorbance with conductivity and tensile strength, etc. Next, so the image below shows a crystal lattice structure. You can assume in this case that all of atoms are the same elements. The distance A to B, A to C, and A to D are all different. This means that the physical and mechanical properties in this crystal will all be different across these different axes. There are three main types of crystalline solids. First is the ionic crystalline solids, metallic crystalline structures, covalent crystalline structures. So, first, let us discuss what is ionic crystalline solids. Ionic crystalline structure are formed of alternating cations, which is positively charged, and anions, which is negatively charged. So ionic crystalline solids, these types of crystals are hard and brittle. They also have high melting points. As solids, they are not able to conduct electricity, but they do when molten or in an aqueous solution. Next is metallic crystalline structures. Metallic crystalline structures are formed of metal cations surrounded by so-called sea of mobile valence electrons. These also be called delocalized electrons, in which they do not belong to any one specific atom, but are still able throughout the entire crystal structure. This means that metallic crystalline structures are excellent at conducting electricity. So next, covalent crystalline structures are formed of atoms at the lattice points of crystal. Each atom is bonded covalently to its neighboring atoms. This network is 3D. Much like the ionic structure, is very hard and brittle. They also have very high melting points and boiling points. These structures are made of atoms rather than ions, and so they do not conduct electricity. Anisotropic properties includes hardness or cleavability, elasticity, expansion properties, electric or thermal conductivity, electric polarizability, magnetation. Modulus of elasticity. An elastic modulus is a quantity that measures an object or substance's resistance to being deformed elastically when a stress is applied to it. So the formula of modulus of elasticity is Y is equal to strain over stress. So now, I'm teaching you on how to solve Young modulus of elasticity. So the formula of Young modulus of elasticity is Y is equal to stress over strain. So the example problems of Young modulus of elasticity is this. Example number 1. A wire 2 meter long and 2 millimeter in diameter, when stretched by weight of 8 kg, has its length increased by 0.24 millimeter. Find the stress, strain, and Young's modulus of the material of the wire. So for example number 1, the given is the length, which is 2 meter, the diameter is equal to 2 millimeter, the radius 2 millimeter over 2 millimeter is equal to 1 millimeter, or 1 times 10 raised to negative 3 meter. The gravitational acceleration is 9.81 meter per second squared. The increased length is equal to 0.24 millimeter, or 0.24 times 10 raised to negative 3 meter. And the mass is 8 kilograms. So the unknown in example number 1 is the stress, strain, and the Young modulus of elasticity. So now, let's solve it. So first, let's solve the stress. Stress is equal to force over acceleration, or mass times gravitational acceleration over pi times radius squared. Let's substitute. The mass is equal to 8 multiplied by 9.81 meter per second squared. So that's Newton over pi times the radius is equal to 1 times 10 is to negative 3 meter squared. So the answer is 2.5 times 10 raised to 7 Newton meter squared. Next is the strain. Strain is equal to increased length over the length. So increased length is 0.24 times 10 raised to negative 3 meter over the length is 2 meter. So the answer is 1.2 times 10 raised to negative 4. So that's the answer for the strain. So next, let's solve for the Young modulus of elasticity. So Young modulus of elasticity is equal to stress over strain. So our stress is 2.5 times 10 raised to 7 Newton meter squared over the strain is 1.2 times 10 raised to negative 4. So the answer is 2.08 times 10 raised to 11 Newton meter squared. Example number 2. A wire of length 2 meter and cross-sectional area is 10 raised to negative 4 square meter is stretched by a load of 102 kilograms. The wire is stretched by 0.1 centimeter. Calculate the longitudinal stress, longitudinal strain, and Young's modulus of the material of the wire. So for example number 2, come on, let's solve. So for example number 2, the given is the length, which is 2 meter, the area, which is 10 raised to negative 4 square meter. The mass or the weight is equal to 102 kilograms. The increased length is equal to 0.1 centimeter, or 1 times 10 raised to negative 3 meter. And the gravitational acceleration is the 9.81 meter per second squared. The unknown is the stress, strain, and Young modulus of elasticity. So let's solve. Let's solve for the stress. Stress is equal to force over area is equal to mass times gravitational acceleration over area is equal to, let's substitute, which is the mass is is equal to 102 kilograms multiplied by 9.81 meter per second squared. So that is Newton over the area is equal to 10 raised to negative 4 square meter. So the answer is 1 times 10 raised to 7 Newton square meter. So for strain is equal to increased length over the length. So increased length is equal to 1 times 10 raised to negative 3 meter over 2 meter. The answer is 5 times 10 raised to negative 4. So for Young modulus of elasticity is equal to stress over strain. Strain is equal to stress is 1 times 10 raised to 7 Newton square meter over our strain is 5 times 10 raised to negative 4. So the answer is 2 times 10 raised to 10 Newton square meter. Example number 3. A mild steel wire of radius 0.5 mm and length 3 meter is stretched by a force of 49 Newton. Calculate A. Longitudinal stress, B. Longitudinal strain, and C. Elongation produced in the body of if Y for steel is 2.1 times 10 raised to 11 Newton per square meter. So for example number 3, come on, let's solve. So for example number 3, the given is the length, which is 3 meter, the radius 0.5 millimeter is equal to 5 times 10 raised to negative 4 meter. Our force is 49 Newton. Our Young modulus of elasticity is equal to 2.1 times 10 raised to 11 Newton per square meter. So our unknown is the stress, the strain, and the increased length. Come on, let's solve. So let's solve for the stress. Stress is equal to force over the area. So our force is equal to 49 Newton, which is given, and our formula for area is equal to pi times the radius, which is 5 times 10 raised to negative 4 meter squared. So the answer is 6.238 times 10 raised to 7 Newton square meter. So let's solve for the strain. So the given formula is Young modulus is equal to stress over strain. Therefore, strain is equal to stress over the Young modulus. So let's substitute. The stress is 6.238 times 10 raised to 7 Newton square meter over our Young modulus is 2.1 times 10 raised to 11 Newton square meter. So our answer is 2.97 times 10 raised to negative 4. That is our strain. So now let's solve for the increased length. So strain is equal to increased length over the length. So therefore, increased length is equal to strain multiplied by the length. So our strain is 2.97 times 10 raised to negative 4 multiply by the length, which is 3. So the answer is 8.91 times 10 raised to negative 4 meter.